Let me thank the organizers first for giving me a chance for coming here and talking, and of course for continuing Fracmeet for so long and so well. Okay, so thank you. Okay. It was working just now. It's coming. Thank you. Okay, it's green again. Okay, so I'm going to tell you about two recent tabletop experiments that we performed in our laboratory. So one of these experiments is, so both these experiments are with clay suspensions, which is a colloidal material, and it ages. Okay, so it shows physical aging, its properties evolve with time spontaneously for reasons I'll tell you about. Now the two experiments that I'm going to tell you about, these are tabletop experiments. In the first one, we looked at viscous instabilities that form when you displace clay suspensions with Newtonian liquids. We see the most gorgeous patterns. I'll show you those. And then in the second part, I'll tell you about desiccation cracks that form due to solvent loss from thin layers of clay. So I'm Ranjini from the Raman Research Institute, and all the work I'm going to tell you about today, the first part was done by Palak. Palak just got her PhD. She used to be my PhD student till last year. She's now in Canada. And this is Vaibhav. He's done the second part of the talk. He also had a supporting role in the first part. He's about to finish his thesis. Okay. So clays are ubiquitous, right? I mean, they're all around us. It's in the ground beneath our feet. It has several uses, like it's used for sculpting, pottery. It has industrial uses. It's an insulator. It has medical uses. Kaolinite K, for instance, is used as an antidiarrheal, and we use it for research because it is a fantastic model system for a soft, glassy material. Now, have you ever wondered what clay looks like? So we just put some clay under a microscope. It's an electron microscope because the length scales we were trying to measure were we wanted to view were really small. This is what it looks like. So it forms a gel kind of a structure, and I'll tell you why it forms a gel. But then it's a very fragile network that it forms, and each strand of this gel that you see here, it is constituted by many clay particles. So there you go. Within a certain concentration regime, clay forms a gel, and it is that concentration range that we'll be looking at. So it forms these gel-like structures that are weak and are held together by screened electrostatic interactions. So you can think of particles with a kind of a debye layer around it, and there's screen charges, and there are some charge distributions that I'll tell you about that gives rise to this kind of a network gel structure. The two main properties that we will exploit in both the studies that I'm going to tell you about are the fragility of the clay. It's a soft suspension. It can be broken up very easily. You just need to take some clay, looks elastic. You just need to take a spoon or a fork. If you stir it, you're going to completely melt the clay. Okay, and aging. So here we are talking about physical aging. The structures, the microstructures in clay, they evolve with time spontaneously, and I'll tell you why they do so. First, let's look what an individual clay particle looks like. So clay particles have sheet-like structures. This is a single inorganic molecule of clay, and they are mainly made of aluminum silicates. So on the top layer here, you see some oxygen ions, and there are also some sodium ions. So the moment you take this molecule and put it in water, the sodium ions are going to diffuse out into the water and form an electrical double layer, right? So you can think of the clay, it has a disc-like structure. So if this is a clay plate, then the faces, they are negatively charged because of the oxygen ions, and the whole clay particle is surrounded by this DLVO layer, the debye layer of positively charged sodium ions, and depending on the pH of the medium, there are these side groups that are magnesium. They get hydrated, so you end up with a disc that has, so it's a plate, okay, the faces are negative and the sides are, the rim of the disc is positive. Okay, so why does clay age? Okay, so when we buy clay off the shelf, okay, from say, Sigma Aldrich in the best case, and we buy it as a powder. And this is what it looks like. Now when you put this powder in water, the clay, the clay granules here, they dissociate into these particle stacks, okay. So these are one-dimensional aggregates, okay. So they think of them as vertical aggregates, they are called tactoids, and so this is what an individual stack looks like. But what this picture doesn't tell you is that these golden discs that you see, these are the clay particles, but in the intergallery layer between the two clay particles, you have sodium ions, right, that come from here. Now the moment you put this stack into water, there's an osmotic pressure difference. As a result of this, the sodium ions in the interlayer gallery, they try to come out into the bulk, and as a result, the clay swells. Okay, so the clay swells, and like I told you, each clay particle has this double layer repulsive layer around it. Now the moment, because of the swelling of the clay, when the double layer repulsion exceeds the interparticle van der Waals interaction, the clay particles, they start peeling off from the edges. Okay, so this is called exfoliation. And this is why the aging happens, because there's this evolution of the microscopic structure of the clay. There are these particles, these tactoids that are swelling, particles that are falling off. Now remember, each particle, like I told you, it has this anisotropic distribution of charges. The plates are so it's a disc like this, okay, with the faces that are negatively charged, and the rim which is positively charged, which depends on pH, but then in the experiments that I'll be telling you about, this is exactly what they look like, okay. These things can be controlled, so it's a fantastic test bed to do all kinds of experiments. Now so these are the clay particles. Now because of their negative faces and the positive rims, they can form these house of cards kind of structures, okay. So it's it can form a percolating network in your entire sample. So that's what we are calling a gel here. And indeed, these are measurements that we did. So if you take a freshly made clay suspension, and you just start measuring the sodium ion concentrations with TW, which is the age of the sample, that's the time since preparation. So you just make the sample, stir it vigorously, then just let it age, okay. So the time at which the stirring has stopped, that is what is TW is equal to 0, which is the aging time or the waiting time. And then you just measure you don't disturb the sample, or at least you disturb it minimally. As you're making the measurement, use a sodium ion sensor, and this is an experiment that has gone on for 28 hours. You can see that the sodium ions are gradually diffusing out into the suspension, and that's what we are measuring. This is from a paper quite long ago. Now this is what a sample looks like. So when you freshly prepare a clay suspension, okay, so you just put the clay in water, you mix it, and then it looks like, so you can see the meniscus here, right? So it's liquid. It's a liquid. It's a liquid that's about 10 times more viscous than water. But then you seal it up, come back the next day after 24 hours, turn it over, it's become a solid. Okay, it's become a soft glassy material. So what you just did here was a viscoelastic liquid to a viscoelastic solid transition. Now the beauty is that it happens spontaneously because of the evolution of the microstructures that I told you about. Okay, and sure enough, this is some rheology that we did. So here G prime are these solid circles. This is the elastic modulus. G double prime are these hollow symbols, that is the viscous modulus. So when you just apply a very small oscillation, just enough to measure the elastic and viscous moduli of this material versus the time of waiting or the aging time, you can see that initially at very low aging times, that is just after you have loaded the sample into the rheometer, your system is a liquid, right? You can see that the hollow symbols are above the solid symbols, but then if you just wait, again you are not disturbing your sample, you wait for about an hour or so, and you can see that the elastic modulus, it exceeds the viscous modulus. So that's where you just, that's where the viscoelastic liquid to the solid transition just happened. And if you go further down in time, which is what we'll mostly be doing, you can see that this is a solid. Okay, so this is very elastic. It's much more elastic than it is viscous. Okay, and so just to again explain what is happening, so at the very low aging times, you can think of them as particles or stacks that are completely, they're not touching. Okay, they're kind of diffusing around, and therefore what you really see is the liquid-like character. But then as you wait, you've allowed the sample a lot of time so that its microscopic structures build up, so that the gel structure builds up. You end up with a house of cards structure that is, of course, it's a rigid structure, as a result of which your system is now elastic. Okay, and this is from another different work that we did. Aging, of course, is very interesting in the material, but this is viscoelastic. It's a shear thinning viscoelastic material. So here we have the same laponite suspensions, but then aged to different times. So you just fill it in the rheometer, wait for 1, 2 and 3 hours, and then shear it in rotational rheometry measurements, and you can see that the viscosity decreases with shear rate, so it's shear thinning. So it has, so laponite, in this case we are using laponite as a model clay. This would work for any other clay particle. Okay, it could work for synthetic clays or natural clays, but these are the two properties that we are going to exploit today. One is its time-dependent rheology, its aging, and the other is its shear thinning rheology, its shear-dependent rheology. And let's see if we can actually control the kind of patterns that we make in our interfacial instabilities experiments, and let us see if we can control the cracking of clay. Okay, so yeah. So this is our first experiment. So the displacement of clay suspensions by Newtonian fluids, okay, in a Healy-Shaw geometry, and like I just told you, we want to see if we can exploit the unique rheology of clay to control the growth of the interface. So this is our experiment. These sky blue plates are big, okay, they are about 30 centimeters in radius, and each glass plate has a thickness of about a centimeter, and the two glass plates have a tiny separation that the separation is because of some spacers of 170 microns that we put in between to give us a little tiny gap that we could call quasi two-dimensional. Okay, and then the top plate has a little hole so that our syringe pump can fit to it and it can inject different kinds of fluids. So the first fluid that we fill here is the clay. Okay, so we take a freshly prepared clay suspension and we first inject it through the syringe pump. We wait for it to evolve because, as I told you, clay microstructures evolve. So we waited, so in every experiment we've used a different clay sample, we waited for it to evolve for different times. So we wait for the clay suspension to evolve different quanta of elasticity. Okay, so each system is elastic, but it's different. The viscoelastic properties are a little different. So we just let the clay suspension settle and evolve, and then we inject the second fluid, which for simplicity in this case, I mean this is hard enough, okay, but then the second fluid, which is the red fluid that you see here, this is a Newtonian fluid. Now it is Newtonian, but it can have different kinds of wettabilities. So the clay suspension, of course, is made in water. Okay, so it is an aqueous suspension. So we've used we've looked at two kinds of interfaces here. One is a miscible interface, in which case we have used our syringe pump to inject water. In the second case, we've injected oil so that there's surface tension at the interface. Okay, so we have the zero interfacial tension and the non-zero interfacial tension case, and then we are experimentalists. We measure things, by looking at them, so that we illuminate the sample from the top, and then we image it from the bottom using a high-speed camera. Okay, so just to again, motivate the problem, I'll just tell you that the outer purple fluid here, that's clay, which is aging, and it is shear thinning. Okay, it's non-Newtonian, and the displacing fluid that we've used is water and mineral oil, and I think if I have done it right in the rest of this part of the talk, water will be in blue and mineral oil, which is our immiscible solvent, okay, or the immiscible displacing fluid will be in red. And as you can see, so this is the viscosity of both these materials versus shear rate, and there you go, so water is black here already, but then this is oil. But then you can see that unlike in the case of the non-Newtonian fluid, these two materials, the displacing fluid, so that's the red material here, the viscosity does not depend on the shear rate that you've applied. So these are our miscible displacement patterns. So the gray thing that you see here, this gray, this is the clay. You're looking at it from the bottom, okay, and so this is where I'm going to be introducing my water, which I've dyed red, so that you can see the interface. Yes. Oh, okay, okay. So, and now this is what we've done. So this is what all the 3 boxes are about. So in the first case, we filled the clay, we waited for an hour. So it's not very elastic, okay. Maybe structures have started developing, but it's really more viscous than it is elastic. In the second system, so these are all separate experiments. We introduce the clay, we wait for 3 hours. Okay, so now the structures have started building up, though they are not very dense yet. So this is elastic, but you know, there's also a viscous component that is quite significant. But after 24 hours, it's like our window glass. Okay, it's a solid. So each are, like I said, I can't reiterate this enough, you know, these are systems with memory, they are aging. So each of these are fresh samples. So my students actually will, you know, inject the sample, wait for 24 hours, come back the next day, and of course we do things like sticking nail polish on the side so that, you know, the aqueous solvent does not evaporate, and then we do the experiment. So let's look at the experiment at 1 hour. So this is when the laponite clay is quite viscous. Okay? But then the viscosity of the laponite clay, it is still less, it is still more than the viscosity of the fluid, the water that is being injected into the laponite. You get a viscous instability, but you can see this is a kind of an odd kind of a pattern. You know, if you look at it very carefully, you'll see that much of the propagation is happening because of tip splitting, though there are a few side branches. Okay, there are really no clearly well-defined boundaries, and if you look close enough again, you're going to see that the fingers actually even start merging into each other. Okay, so this is a pattern that we call a dense viscous pattern, and then let's look what happens when we waited a little bit longer, when the clay suspension was a little more elastic than it was in the first place. Okay, so I don't know if you're noticing it, but you can see that the propagation is already becoming faster, and you get these beautiful patterns that have not tip splitting at all, but you have side branching. Okay, so why does side branching happen? Because the fluid outside is viscoelastic, and as you're driving in the water at rather high driving pressures, okay, there is a competition that goes on. On the one hand, the tip of every finger is trying to shear thin the clay suspension, okay, that it is invading, and on the other hand, there's this driving pressure of water that is trying to broaden the fingers, and that results in the shedding of side branches. And as you can see, so this is the first, you know, so you wait for a little bit of time and you can see that the elastic effects are kind of becoming more and more prominent. Now let's look at our, yeah. Yes. You wouldn't see anything moving. Yeah. So see, this is like, you know, you could do this with your naked eyes. Okay, I mean, we're just looking at the interface. You know, we're looking at the morphology of the fully developed pattern here. Though we've done a lot more than that, we've even, you know, kind of tracked individual fingers, but I'll not have time to tell you about that. Yeah, so here it's really the, you know, so we're really looking at length scales that are this big. Okay. Yeah, so we call these dendritic patterns, though they may not exactly be dendrites, but then the reason why we are calling them dendrites is because of the predominance of the formation of side branches. And here's the cracking, which you saw a lot of. Okay, so here, remember, so this is a very aged suspension, it's very elastic. So when you're driving the water through the suspension, you know, the elastic stresses that are being built up, they have to be released, and they have to be released really, really fast. Okay, so this happens by the evolution, you know, by the formation of these crack patterns, and as you can see, there are a few primary branches. They are all very narrow. Okay, they're really, really narrow. They are narrower than all the other branches that we formed here, and there are some stresses that are also being released perpendicularly. So you have these perpendicular offshoots that are very, very typical of crack patterns. But there's one thing that I cannot stress enough here. Just remember that, you know, we've got this kind of zoo of patterns, and I'll show you more when we change the miscibility at the interface. it's the same suspension, okay? It's chemically the same suspension, it's just doing its own thing, we've just waited. So the only control parameter here is just waiting for different amounts of time. What we have in that gray thing, okay, it's the chemically identical sample. This is a viscoelastic fracture. Okay, and now of course we've done it at many other different ages, and you can see that as the age of the suspension increases and as you inject water, you can see that you have this kind of a smooth transition from this kind of a dense viscous pattern through the dendritic kind of pattern and then all the way up to viscoelastic fractures. Okay, so that was a miscible displacement case. What happens if there's some surface tension at the interface? So what we do here is instead, so this is the same clay that we have. So here this is clay that has been aged only up to an hour, and this is clay that has been aged up to 24 hours, and we inject oil. Okay, it's a mineral oil, it looks red because we have dyed it with Nile red, and then let's see what happens. These experiments are at the exact same flow rate as I used in the miscible displacement case. Okay, initially nothing. Okay, this is almost like a viscous displacement. Okay, so you have this interface, a stable interface that grows, and now you can see that there are some tiny protrusions that are beginning to develop. Okay, so after that initial stable growth, you see some fat protrusions that develop. We call this the flower pattern. And one thing you would notice is it's taking forever to propagate. Okay, that is because of the stabilizing effect of surface tension. Okay, so we call this the flower pattern. Again, it's the same clay as before. All we've done is we've changed the miscibility of the two fluids at the interface. And then you wait much longer, and then again you introduce oil in a fresh sample. You can see it changes. Okay, so that is because at 24 hours of age, the clay has many elastic structures, right? So as the oil propagates through these elastic structures, it has to break up these structures. Okay, so lots of elastic stresses are being released. There's a huge energy cost, and that is the reason why you find these ramified structures. Okay, they're still trying to kind of smoothen out, because that's what surface tension does, but you still have this kind of a branching pattern where every finger is much thicker than you saw in the case of the miscible displacement pattern. And I'll just tell you, so we call this jagged patterns. I mean, this is not something that we came up with, but this is something that was seen by Doug Durian and group when they invaded foam, shaving foam with air. Okay, so that was also an immiscible displacement. Shaving foam is very elastic, and they saw the same kind of pattern. Okay, and again, even for these, I'm sorry about that displacement spelling. So even for the immiscible displacement experiments, we've done it at several different ages. So this is with age, sample age, the clay age increasing, and you can see first, for the younger samples, you see that you have the stable interface that eventually develops this flowery petal-like pattern at the interface, and then you move on to the jagged patterns that I just showed you about. So what to do with these patterns, right? So let's see. So we have used the same clay, we've just waited for different amounts of time. We've also changed the flow rates of the driving pressures of the Newtonian fluids, as you'll see. Okay, and we've got this zoo of patterns. So let's try to kind of put some numbers to the patterns. So what we've done here is we've defined a quantity called an areal ratio, which is the AP here is the area that is covered by the fully developed pattern. Okay, so once the pattern is not really developing anymore, that's our T is equal to the end of the experiment, and that the area that the pattern covers, that the fully developed morphology covers, we call it AP, and we divided it by the radius, by the area of the circle of the minimum, the smallest circle, okay, that can kind of enclose the entire the pattern that we see. Okay, and of course there are the usual things to calculate, which is the finger frequency. So these are the number of frequencies within an annulus, okay, at the edge of the pattern, and of course the finger width, which is the width of the individual fingers. And then here is all our data here. Okay, so this is all our surface tension 0 data. So these are the experiments. These are just snapshots from the experiments. This is the fully developed pattern morphology when the age of the clay suspension goes up and when the clay suspension is being invaded by water, and you can see how the coverage changes, right? I mean, you don't really need to put a number to it. I mean, you just need to look at these pictures. And then here again the clay suspension age is increasing, but then you've introduced this immiscibility at the interface, and here are our patterns. And here are the numbers that we've calculated. So you can see that the finger widths don't really change in the two cases, apart from the fact that, you know, in the miscible displacement cases, the fingers are way narrower, okay? And in the case of the immiscible displacement experiments, you can see that the finger frequency doesn't change very much either, as you can see here. That's because, again, like I said, that's the stabilizing effect of surface tension. But when you use the miscible, when you did the miscible displacement, you can see that the finger frequency decreases very rapidly as you age the sample. Okay? Yeah.
Some cases it is clear what is small r, but in this case, in your leftmost picture, no, this one, the bigger one.
This one.
So how are you defining small r?
I mean, there is no small r here.
Okay.
Sorry, that was a different analysis. Yeah.
Oh, sorry.
Yeah. So all we do is we count the pixels of the, you know, the pattern, and then, you know, we just have a big R here. I'm sorry, that is from some other talk.
Oh.
Okay. Okay. So that was when we were looking at the growth of the longest finger, which I'm not really going to tell you about. Yeah. So yeah. So then, you know, and as you can see here, so again, reds are oil and blacks are the water displacement experiments, and you can see that, you know, you get much more compact patterns when you use oil rather than, you know, water. And then now there's something else that you can do. So you see this zoo of patterns because you're really, as the Newtonian fluid invades the outer suspension, it's really changing the rheology of the suspension, right? Because here you're displacing a suspension that is aging. You can also change the rheology because, you know, the rheology is dependent on the shear rate, right? So what we do here is we again change the rheology of the clay suspension by changing the shear rate of the water or the oil that is invading the clay suspension. Okay, so that's our data. So this is with flow rate increasing. So here all the clay, for all these experiments, we waited for 24 hours, okay, for the clay to become elastic, to settle down. Okay, and then we inject water here and oil here, but at increasing flow rates, just to increase the shear rate. And you can see what we get here is exactly, you know, it's the inverse of what we got when we aged the sample. Okay, so as you increase the flow rate, you can see that, you know, because this was a highly aged sample, you started off with a viscoelastic fracture, then eventually you moved on to a dendritic pattern. We didn't quite see dense viscous, but then, you know, these are things that one can do by just changing the age of the clay suspension with which we started. Now similarly for oil, because, you know, the clay outside was highly aged, when we introduced the oil at a very low flow rate, you get the jag pattern. But as you increase the flow rate more and more, you can see that because of shear thinning of the outer clay suspension, the viscosity mismatch between the oil and the water, they kind of, that mismatch reduces, as a result of which for a very long time you can actually stabilize the interface before you see these little protrusions coming out in the form of a flower pattern. So again, we've done the same kind of analysis, and again we see that, you know, the finger, you know, because you have really the same patterns here, only in the opposite direction. Before, we were really plotting these quantities versus the age of the clay suspension that we were displacing. Here we have plotted it versus the volumetric flow rate of the Newtonian fluid that is displacing the clay suspension. Okay, so now, okay, so we have lots of patterns. Can we somehow, you know, is there anything that we can predict? Can we control these patterns? I mean, clearly we can, right? We control the pattern just by controlling the rheology of the outer face as well as the flow rate of the Newtonian fluid, the displacing fluid. And then, so here we've plotted this areal ratio versus the product of the finger width and the finger frequency, and sure enough, regardless of, what the flow rate of the displacing fluid is, what the rheology of the outer fluid is, or, whether you are using a miscible displacement, whether your experiments are a miscible displacement experiment or an immiscible displacement experiment, you see that these two quantities are linearly correlated. Okay, and then this was, we had to kind of end this thing somehow. So we thought, why not let's make this three-dimensional phase diagram where the, yes. I mean, okay, I told you this was, yeah. Yeah, perhaps, I mean, as you can see, all the quantities at the larger F into W's are really oil, right? So there will be small changes. But then what we are trying to say is that this area can be kind of, described by this product. I mean, because these are the two length scales that we can really find. But, as you know, for the oil, so initially there was no finger, right? Because it was just a stable displacement. So, I mean, all this is very, very approximate. So, I mean, the message really here is that, you're using the same suspension, okay, but you can control the morphology of the patterns just by, waiting for longer and longer times. So then, yeah, we managed to kind of segregate this pattern, segregate all the patterns in a kind of a phase diagram where, and we did this in terms of the logarithm of the areal ratio. So if you probably give me the logarithm of an areal ratio, I can tell you that, okay, if this is the Laponow, if this is the clay outside and if this is the material that you're injecting into it, this is the pattern that you get even without seeing the pattern. Okay, and I just told you about the fully developed morphology, so we also really looked at the temporal growth of the patterns. I'm not going to have time to tell you this, but then obviously the temporal growth of the patterns do determine their fully developed morphologies. And like I told you, in the case of the dense viscous pattern, we see a lot of tip splitting as the age increases, as the laponite, the clay age increases and you get, the clay becomes a little more elastic, you see a lot of side branching and then eventually cracking. And when you have an immiscible displacement, you start off with a stable interface, you form these protrusions, and then you get this kind of a ramified jagged pattern. Okay, so we've really looked at these by looking at the propagation of the longest finger, and then we have this other very colorful figure, where again, just by looking at the velocity of propagation, okay, you can kind of segregate all the patterns. Now, like Vani pointed out, this is not really much, but this is the message of the whole thing. I'm showing you this because these patterns are so gorgeous, I could just look at them all day. Very difficult to really, do a simulation and understand them, but I just thought, this is a meeting on cracks and upscaling, and I could say that, I can predict the patterns that will happen if I know the rheology outside. This is an obvious statement, but here I'm controlling the rheology outside. Okay, so the areal ratio and the pattern propagation velocity are both very sensitively dependent on the rheology of the outer viscoelastic clay suspension, and of course it depends on the wettability of the two fluids and the injection flow rate of the displacing fluid. The suspension age used here, we are really using the suspension age, we believe for the first time, as a control parameter to study the growth of unstable interfaces and to control the growth and for the onset and growth of the unstable interfaces. And these are some of the papers that we wrote based on this. Okay. So I'm going to take a little break here because I'm going to now move on to something related, but it's a different set of experiments. So patterns in nature, of course, are ubiquitous. Okay, you have the tree that branches, this is the branching morphogenesis in a vertebrate airway tract, and why do we have branches? Because it is optimizing some function. It could be a different function, but branching optimizes this function. And then of course I told you another beautiful pattern that occurs. But those were, what we saw in the lab. This is from the seminal paper by Safman and Taylor. So here you see tongues of air that are invading glycerol. Okay, so patterns are beautiful for an experimentalist, There's another kind of pattern, okay, and these are desiccation cracks, okay, cracking of soil, okay, clay of course is a major ingredient of soil. So there are some, model soils that we made in the lab and we tried to do some experiments with. So why do cracks form? I mean, we have the experts sitting right here, but then so you can, here we are really thinking of, clay as these, in this cartoon, it's spherical, these are like circular, they look circular here. There is this water phase, okay, so you can think, and in our case, of course, you have a clay gel, so the particles are touching, okay, but then you have water in the pores of this gel, right? And then as evaporation happens, okay, you have a capillary contribution that develops, okay, there's a vertical consolidation of the material, the sample becomes thinner, okay, you have this meniscus that forms, the pore pressure goes up, because remember we are talking about really, really tiny pores here. Okay, these are like maximum micron sized pores, so that's 1 over R, so the pressures are huge, okay, you could have capillary suction, but in any case, there are tensile stresses that develop in the plane, the top plane, and then you get surface cracks that form, and this is a picture that I got from here. So now let's see if we can control crack formation in these clays, okay. So like I told you, when you just make a clay, it is a viscoelastic liquid. You let it evaporate, there is solvent loss, so obviously, the concentration increases, you end up with a viscoelastic solid. You evaporate it a bit more and then it starts cracking. I'll show you a video in a little while, in a little bit actually. And then there is another way in which you can go from a clay suspension being a viscoelastic liquid to a viscoelastic solid, and that is just by controlling the physical aging, which is what we do in this system. So not only do we have solvent loss as we do in a usual desiccation experiment, here we are also controlling the physical aging of the clay suspension that is cracking. And just to remind you, at very low ages of the clay suspension, you can think of these clay, the charged clay particles as all being, individually they are diffusing around in the water medium, but at higher age they form these house of cards structures, which is a rigid structure, it's a gel-like structure, and therefore your sample behaves like an elastic solid, but it's a soft solid, which means that it's fragile and you can very easily, it yields very easily. Okay, and how have we changed the aging behavior of the clays? It's very simple. We've changed the interparticle interactions, and because these are charge stabilized colloids, it's very easy to change the interparticle interactions and you can completely stop the aging process. Okay, so when this happens, you've reached what is called a state of kinetic arrest. Now you can just add a little bit of a sample that I'll tell you about, and you can completely melt that kinetically arrested phase. So, and that compound is TSPP. So we use a tiny amount of tetrasodium pyrophosphate as an additive, okay, and what happens then is when you add it to your clay suspension, the P2O7s, the pyrophosphates, they go sit on the positively charged rims. The positively charged rims now become negatively charged, okay, and that completely fluidizes your system over the range, over the experimental time scale. And of course, there was the second experiment where we did not use any additive at all. Okay, so you got the usual clay gel, and in the third experiment, we put common salt. And remember I told you these clay particles, they have a debye layer around them. So when you add the salt, what do? You're basically shrinking the debye layer. So then the particles, they can now attract, okay, because of the negatively charged faces and the positively charged rims, you form gels that are denser than you would have formed had there been no common salt at all. Okay, so these are the three kinds of samples we've made. So you can think of them as going from repulsive particles all the way to highly, highly attractive particles as you add salt. Okay, and sure enough, yes.
To change it all into completely negative, you couldn't, it is also pH dependent. Across the isoelectric point,
we are way away from the isoelectric
so
point.
You are,
no,
so
we are not worried about that at all, yeah. So I mean, in all our experiments, so we are really at, pHs of 7 or so. So whatever you do, your pH is never at the isoelectric point of 11.
Lapunite in water would be around 10 generally.
Right.
How did you get 7?
You can put a bit of, acid and stuff like that. Yeah.
Okay.
Yeah. Right. Because we wanted to stay, because we understand that we are adding, we are incorporating additives and stuff. So we wanted to make sure that we are away from that isoelectric point.
Right. Thanks.
So this is the rheology data right here. So here, this is the data that you get. So this is the complex viscosity which we get from oscillatory rheology experiments versus the aging time of the clay. And as you can see here, we've continued up to 300 minutes. And for the sample in with TSPP, which was this repulsive sample, the non-gel forming sample, you can see that the viscosity doesn't change. It's actually a little more viscous than the viscosity of water. Okay, it's about 10 millipascal seconds, but then when you didn't have an additive, okay, which is here, you can see that initially not much happened. So you had a viscoelastic liquid, like I told you earlier. When you mix clay with water, you end up, you first make something that's about 10 times more viscous than water, and then it starts aging. So that's what you see here. But when you added the salt, it's a solid from the beginning. Okay, so when you added the salt, immediately you had these debye layers that started collapsing, the particles came together, formed these aggregates, formed the gel, and we started measuring this, as you can see from 0.2 minutes, okay, it's a solid, okay. So now let's see how these crack, and because we know that it's really the elastic samples that are going to crack within a time scale that's reasonable. So all the experiments that I'll show you after this are done with the sample with different amounts of salt. Okay, so this is the experiment that we've done. We wanted to look at the onset of the cracking process, and this is we made a box in the lab. Okay, this is the sample. The sample is put on a transparent weighing scale. Okay, we can control the temperature and the relative humidity. The relative humidity is controlled by a saturated salt solution. So in all these experiments, the relative humidity is maintained at 27%. There's a heating element, and everything. The temperature is controlled using an Arduino controlled relay. Okay, and then we have illumination here, so we can look at the cracks. We have a digital camera, okay, so we can image the cracks. So this is a high-speed camera, though these experiments that we've done, for all the solvent to evaporate, it takes almost 24 hours. Okay, so and the onset of the crack that we've seen. So we really look at the sample as it's drying. We look at that instant at which the substrate gets exposed, okay, because of cracking, and that is our crack onset time, and we compare that crack onset time with microindentation measurements that we've made in an AFM to look at the elasticity of the sample layer. It's a partially dried sample. So here's what you do. You take the sample, stick it into an AFM. Okay, so there are these desiccation cracks that are forming, and when we tried doing an AFM experiment with just this sample, the capillary attractions were so high we thought our AFM would break. So we put a little layer of oil, okay, and then we made the measurements. So this you can see is the cantilever and the AFM tip, and this is now the magnified image you can see. So here's our, it's a pyramidal tip, it's a silicon tip, and then this spherical thing that you have here, we think that's what the oil does, it goes, because of surface tension, sits like that around the tip, and then we do this in the contact mode. It's a microindentation measurement, so we go deeper and deeper and deeper, and we measure the force versus indentation curve for different clay suspensions, different ages, different salt concentrations, and so on. And now, so this is a 24-hour video. So nothing happens in the first 9 hours. So this is our Petri dish with the clay suspension image from the top. Nothing happens initially. Okay, and then so we'll start the video at 9 hours, and we'll I think finish it in 9 seconds or so. So that will be like 15 hours of experiment. Okay, so you see, I don't know, I mean this might have been a bit fast, but initially it shrinks from the sides, from the edges, okay, of the Petri dish, and after that you have these cracks that propagate tangentially to the boundary, and then you also have a few radial cracks that form. So okay, so then so here are our cracks. Okay, so these are snapshots from the same image, and like I told you, our cracking sample, this was on a weighing balance, right? So we could actually take the weight all the time. right? And then this is what we see. So the weight versus elapsed time. So as you can see, this goes on for a long, long time. So this blue curve is the weight versus time. You can see there is, and this is the evaporation rate that we've calculated. So there is a constant evaporation rate zone, before which, capillary pressures become huge and, everything happens together and very fast. But then all our data, including the formation of the first crack, happens here at the constant evaporation rate regime. Okay? Yeah. And then this is really not terribly relevant anymore, but I'll just show you some experiments because Vaibhav did these, so he used a digital image correlation technique. So these are again the kind of the processed images of the Petri dishes seen from the top. So what he did was he took the Petri dishes with the clay as it was cracking, he put some pepper powder on it, and that was, he did a kind of a particle imaging velocimetry, and then he calculated the strain fields by looking at successive images, okay. So this was done with a code that, we could find NCORE, okay, it's a MATLAB code that is freely available in the internet, and these are the 3 sets of experiments. In this case, the number A, this is what I've been telling you about, you have the Petri dish and you have clay and you just let it dry. Over here, what Vaibhav has done is, he's just coated the rims of the Petri dish, okay. So there is really no adhesion with the walls, and you can see already that even though there is a crack that forms much, much later, there is hardly any cracking in the system when you just coat the rims with a little bit of grease, okay. So, but what happens is, the sample shrinks, okay. So because there's no, right. So it just, it shrinks, it doesn't crack. Now in this case, the third case, he's coated the whole Petri dish with grease, and as you can see, there's even after 20, 30 hours practically, there is absolutely no cracking at all, there's only shrinking. Okay, it just detaches from the wall and shrinks, yeah. Okay, I think I'm almost done, I think, yeah. So the cracks will only form if the sample adheres to the boundary. I mean, this is kind of obvious, but then, this is so cool that I thought I'll show you. And then, so this is the data that we have here. So this is temporal data, okay. So this is the same sample, you're just letting it evolve. These are snapshots from the drying process. And as you go from top to bottom, you're increasing the elasticity of the suspension because, this row, this is with samples with the TSPP, which is very, very liquidy. This is with, no additive at all, this row. So therefore, it is kind of a viscoelastic liquid that is evolving into a weak viscoelastic solid, and this is the sample with salt. So, this is highly, highly elastic pretty much from the beginning, and it cracks a lot, okay, and you can see the different, how different the patterns are, right. So as you become more and more elastic, the cracking is, it's a lot more, it's, you have more cracks, it happens faster, and so on and so forth. So now we calculate the crack onset time. I told you how we do it. We define the crack onset time as the time at which the substrate can first be seen. I'm not showing you the raw data, but then as you can see, as you increase the sodium chloride concentration, crack onset time goes down quite a bit. Now here we have a narrow range, so the CL here is the concentration of the clays that we've used. As you can see that the range is rather narrow, which is why, I'm not going to make a song and dance about any kind of, trend in that narrow regime, and the reason why we've used this particular range of clay concentrations is because this is where clay forms a soft glass. If you add any more clay, you're going to get into a nematic phase, okay, which we wanted to avoid because we want to eventually use the poroelastic model. For that, we want a gel. Okay, now these are the final dried patterns. Again, as you go up here, on the y-axis, your clay concentration is increasing. That means your elasticity goes up. And here we are increasing the additive concentration. So again, you are going from TSPP, high quantities of TSPP through zero additive to high concentrations of sodium chloride. So you also are increasing elasticity as you proceed in this direction. So as you go to positive X or positive Y, you are increasing the elasticity of the drying sample, and sure enough, for the highest elasticities, you see the maximum cracking. You also see that the cracking happens the earliest, okay. And here's the surface crack ratio, and again you can see that it's just what I told you, that as you increase the salt concentration, you can see that cracking happens much earlier, okay. So initially, of course, you'll see, I mean, there's really no cracking, okay, when you are using TSPP. So these points here are really, we are really looking at the substrate being exposed not because of cracking, but because of lateral shrinkage, okay, from the boundaries without the formation of cracks. Okay, so here's our result from the micro indentation measurements. So this is the force indentation depth plots that we have for different, the same clay concentration, but with different sodium chloride common salt concentrations. This is just representative data. We've taken hundreds of data points here, okay? And as you can see, probably because of that spherical approximation of the tip that we made, it does fit to a Hertzian model, and it lets us measure this, it lets us estimate the Young's modulus, which we've plotted here. Okay, and as you can see that as you increase the concentration of clay, so as you increase the elasticity, the elasticity that as you increase the age of the suspension, the measured elasticity in the micro indentation experiments do increase, and as you increase the salt content in the sample, again the measured elasticity increases. And okay, so this is just representative data at two different elapsed times since the the material was loaded into the Petri dish, and so this is for 14 hours, this is for 11 hours, and again this is just to show that the data at 14 hours shows you larger, if you can call this a film, I don't know, I like calling it a layer because it's not really a film in that sense, it's a little thicker than that. So for the data at 14 hours when there's been more solvent loss and there's been more aging, you can see that the elasticity evolves much faster, okay, as you change the concentration and than in the case of the younger sample, okay. And then we have done this, this is all very half-baked yet, but then we used a poroelastic model. You heard a talk on poroelasticity yesterday, and I think there was one or two that I missed earlier. So, so we used a poroelastic model. We use a boundary condition, which is the Darcy's law, to give us the gradient of liquid pressure at the upper surface of the gel, and using that you can calculate the stress, the in-plane stress at the upper surface, which is basically, it goes as the elasticity of the sample, the time, okay, at which you are measuring this elasticity, the volumetric, the evaporation rate, and the height of the sample, which in this case was about 7 millimeters. And then in that we incorporated the Griffith's criterion for the formation of new surfaces because of crack, and you have to believe the algebra here. Sayantan is asking me to hurry up, but eventually Tc is the time, okay, at which sigma is equal to sigma c, that is the onset stress at which cracks start to form, which gives us a Tc, which is the crack onset time, which we just measured in our imaging experiments, and we see that that goes as 1 over root of the elasticity. So Tc is something that we measured from our visualization experiments. This capital E is something that we measured from our indentation experiments. So we plotted these, okay, so here Tc is plotted against 1 over root over E, and well, I mean, not the best fit because cracking is a process that has a very large distribution in onset times, but we do get a kind of a linear fit which we like to see, and therefore I'm showing this to you. Now there are of course a few outliers, or maybe before I talk about the outliers, let me just tell you. So then this linear fit here gives us a slope, okay, and from this slope we put in all the right numbers. So here h is the height of the sample, a is the thickness of the width of the crack, and we know what the evaporation rate is, and this lets us estimate a fracture energy of about 1000 joule per meter square, which seems to indicate that this is a highly ductile sample. So when it cracks, it tries to resist cracks for a really long time, but then it deforms, and then eventually gives way. Okay, now we get back to the outliers here, these red points here, which are completely outside our, the prediction, the predictions of our toy model, and these are these samples. So this is a very well-known phase diagram of laponite suspension, which is the clay we are using here. Okay, this is the reference. So this is plotted, I'll just take one more minute. So this is plotted, okay, so this is the sodium chloride concentration, which is again what we are using. This is the clay concentration, and these three samples, and this big area in the middle here, this is the part where you're forming a gel. Now the red points here, these are really very, very close to the phase boundary between the gel and the nematic the nematic gel-like sample, and this is when the sample is fresh. So as the desiccation happens, as the water evaporates, these 3 samples, they are thrown into this gel phase, okay. So you can't really use the poroelastic model anymore, okay, because it has, the particles are kind of, they self-assemble in a completely different way. Okay, so what we have shown here is that, again, this is another experiment, is desiccation, not pattern formation in the interfacial pattern sense, that we've used clay aging as a control parameter to modify the sample cracking. We show that the poroelastic models kind of work as long as our sample is in that soft glassy state, and this is the group as we are now. Thank you for your attention, and I'm sorry I took a lot of time. Yes.
Very nice talk and the images. I was curious to know in your samples as they are drying, how would the patterns look if you take those different stages of drying and then inject this oil? And the reason I'm asking is, in this environmental sciences, there's a lot of interest in contaminant fate and transport,
right,
as to how these oils, they transport from soil to
right.
this.
Thank you. I mean, that's a great suggestion. We'll do it right after I go back.
As the soil is actually desiccating or it's losing, how does the oil actually come up? Because that fate and transport seems to be a very thing that. So I'm just curious, because you're sitting on all these samples.
Yes, that's an easy sample. So yesterday we heard a talk where there was a brittle fracture that was propagating, and then just putting a little bit of water, lubricates the whole thing and completely changes the crack. So thank you for the little nudge. We'll do that
as a function of percentage of hydration. How would these patterns? I think that I was very curious.
That's an easy experiment, but a very interesting one, as in all soft matter experiments. Thank you.
Other questions?
So, Ranjini, thank you for a very beautiful talk. My question was that, see, you are taking the first appearance of crack as the time when the substrate is exposed. However, I would assume that it certainly depends on the height, and so instead, it's just a suggestion. Think of it that when you write TC as proportional to, you put everything else in a first bracket and put 1 by root E,
right,
which you measured. So that's fine. But I think maybe it is right to include H in that other thing, because there is a lot of work on,
of course,
the height is definitely a parameter.
Right.
If you started with just when the crack appears, that is certainly has got nothing, because cracks are propagating from top to bottom, right? So, I mean, that's one suggestion.
Yeah, so I can, actually you're completely right. And like I said, this is still very half-baked. Okay, we'll probably also look at different heights, but no, so see, the thing is, look at the time over which it dries.
I know.
You see? So yeah, but I agree, that would be a much more careful experiment.
At least put height into your E factor,
we could do
because
that
is a very important factor which will determine your TC.
Right.
So that
I agree, and for that we need more heights, which we are doing now.
Yes, that's number one.
Right.
Number two, did you particularly see, apart from putting NaCl, which is changing your entire thing into this, so I mean, did you do any kind of SEM to see how the particles, the laponite aggregates have arranged themselves because of the effect of NaCl, as a test experiment without that?
No, we did that.
Yes.
So we did SEM. Okay.
And did you see the effect of NaCl in any way changing the aggregation?
Oh yes, absolutely. So that picture that I showed you at the beginning, that's with a lot of NaCl and after waiting for a very long time. So you do see that. So I don't have all the data here, but I can show you, they're there on my computer. But yes, you do form much more, less compact. The concentration of the clay could be the same, and you do form gels, okay, because clay, given the charge, the distribution, the charge anisotropy, if you wait long enough, they do form gels. But if you
Yes,
don't
yes.
put any salt at all, then you do see, you know, a much more sparse network than you would if you put a gel, than if you put a salt. So a network with salt, for instance, it will also have lots of flocculated clay particles.
No, but that would also depend upon the weight percentage of any
Absolutely.
of lapunite itself.
Right, but we are really, no, the weight percentage that we have, we are working within a very, very narrow regime.
What was
You know?
your weight percentage of
So
lapunite?
the soft glassy suspension, so we
Less
started
than
with the soft glassy
1%.
suspension, yeah. So that, you know, it kind of, you know, so 1.75 would be a low estimate, but that it's really between 2 and 3.75%
Yeah, yeah.
weight by volume. So the wiggle room that we have is very, very limited.
small.
So, you know, we can really change things by using additives. I'm almost done. I know the clock is 5 minutes fast, sorry. So yeah, so we can put salt and you can actually see you have the same amount of clay, you have the same age of the clay, but then, you know, you get much more dense networks when you use salt.
And finally, can I ask just one more question?
Yeah,
Or is
quick
it-
one.
Okay.
Yeah. So NaCl, can you just say why it should be circular? Because the effect of adding NaCl, I was clearly seeing that you had, you know, first the circular crack was forming, the primary crack, apart from coming away from. So you have any explanation for that?
Not right now. Not right now, but that is something we see, you know, I mean,
know, I
it's
can
just
see
something, you know, I haven't really wrapped my head around. It's all, it happened over the last, I think, couple of weeks or so. So,
Thank you.
okay, thank you for your questions. And sorry, I don't know if it's.
Okay, so yeah.
Hi, thank you very much. Super interesting. I was wondering, in the very first part, when you showed this transition from this type of more compact, the dense viscous patterns to the thin ones.
Oh,
So that was with a
it didn't
miscible.
come back.
It was with a miscible fluid, right? So water entering the laponite, right? Yeah, up there.
Yeah. Can you please repeat? I was.
Okay, so in the top
Right.
row there, so all of those are with the miscible fluids, right?
Right.
So do you see in the time scale of the experiment actual mixing, so like the water changing the rheology of the defending phase?
We have stopped just before that.
Okay.
You know, there you do see some dye kind of, you know, dissolving, but then, you know, because the spatial details of the, you know, so once that mixing starts, we just stop the experiment, and that's what we are calling the fully developed morphology. The Peclet numbers are very high here.
Right.
So, okay.
Super. Thank you.
Thank you.
Okay, if there are further questions, we can discuss over coffee. So let's thank Ranjini for a wonderful talk. Okay, so our next speaker is Professor Vijay Kumar Chikadi from ISAR Pune. So he'll be telling us about identifying structural defects that govern the relaxation of amorphous solids. Sorry, there is a change, my mistake. So the coffee is right now, and Vijay's talk will be from 11.
Hello, mic check, 1, 2, 3. Mic check, 1, 2, 3. Mic check, 1, 2, 3.
Okay, so welcome back. So our next speaker is Professor Vijay Kumar Chikadi. I have already introduced him once. I'll do it again. So he is from ISAR Pune, and he will be telling us about identifying structural defects that govern the relaxation in amorphous solids.
Thanks, Shanthan. First of all, I'd like to thank the organizers for this invitation and this opportunity to present this work to you. Yeah, so let me start with introducing myself. Many of you are, we are meeting for the first time. My name is Vijay Chikadi, and I'm an experimentalist. We are at Indian Institute of Science for Education and Research in Pune. That's where we are. So the movie that you're seeing here is actually data taken from experiments. So what is being done here is this is a dense colloidal suspension, and we are shearing the suspension. Okay, as we shear, we see that there is plastic deformation in this in the colloidal glass, and what you're seeing here is just how this plastic deformation occurs or propagates as you strain the system. And this is what I'm going to talk about. So the title of the talk is Structural Origin of Relaxation. I'm not only going to talk about sheared systems, but also quiescent systems. So what we are looking at is relaxation in these systems, and how do they connect to, is there a structural origin to the relaxation? So this is what I'm going to talk about. The work that I'm going to present today is mainly the work of a PhD student, Ratima Nisi. And most of these ideas that I'm going to present today are based on the theory that was provided by Sarika and a student. So they are in NCL, and we have a long-standing collaboration with Peter Shah. So these are the people who were involved in this work. And yeah, let me start with this slide. It only tells us that the mechanics of solid has a very long history. It goes back to the times of Da Vinci and then Galileo. If you look at the manuscript, they try to understand how these different kinds of material respond to applied stresses. Okay, so they made in some of their manuscript, they made these kind of drawings. You can see here the beams. How do they bend in response to applied load? Okay, so this was probably they were trying to understand the architecture, or in the context of constructing structures. These were important. And also, once again, in the manuscript of Galileo, you can see that he had these thought experiments how to estimate the strength of a pillar column, or even a rope like this. Okay. So I mean, this is this slide is also to cheer myself that in the age of quantum information, there are several questions that are still unanswered. We take them for granted. I mean, these are essentially things, you apply stress and the material breaks, deforms. We take it for granted without realizing the beautiful physics that is underlying these processes or these phenomena. And I tell my students again and again that even though we are in quantum information age, there are several beautiful problems in physics that are not understood, and this is one of those problems. And I'm going to tell you a little bit about what we have discovered about these things in our experiments. Yeah, so the experiment is very simple. The problem is very simple. You take an elastic solid, you apply stress. We are looking at disordered solid. You apply stress on this, and this is the kind of macroscopic response that you see in the system. On the y-axis is the shear stress, on the x-axis is the strain. For very small strains, there is a linear increase in stress with the strain. So that is and then Newton, and then after a certain strain, there is nonlinearity. Nonlinearity sets into the system, and there's a yield point beyond which a material either flows like a liquid or it breaks down if it is very brittle. Okay, so this is generic, and this is a behavior that you see in a variety of materials. And there's no need to emphasize why we are studying these problems. I mean, this is a fracture community. I don't have to really explain. There are these catastrophic failures which we want to understand them in a better way. So our approach is, I mean, this is more of a macroscopic picture, like, our approach is to understand this problem from a microscopic perspective, what happens on a particle scale. Starting from there, like, how does how does deformation propagate to macroscopic length scales? And yeah, so why disordered systems? I mean, if you look around us, like, there are a lot of materials that can be classified as disordered rather than ordered materials, okay? And once again, it's a big umbrella of material. You can see that there are a variety of materials that are classified as amorphous solids, and the length scale ranges from nanometer to centimeter scale. So this is a big umbrella, and then the hope is that by studying one of these systems, we can understand how the other materials also deform. So that's the motivation for us. So even before I start talking about disordered systems, let's take a moment to look at, like, how ordered systems, ordered solids deform. So our ordered solids are generally made of these defects, and when you apply stress on them, this is what happens. So the movie that is being shown here were the experiments that were conducted by Bragg and Bragg and his collaborator way back in 1950s. What you're seeing here is this is a bubble wrap, which is created on a air-water interface. You just put bubbles and then, like, compress them, like, go to high densities. They form these crystalline rafts, okay? And then these crystalline rafts show many of these defects that you find even in atomic systems. And deforming these kind of systems and then seeing, like, how deformation occurs on a particle scale is very easy. So as you, like, deform the boundaries, you can see that there are defects that move like quasi-particles, so from one boundary to the other boundary. So this is, like, a dislocation picture. Now we would like to ask whether one can extend this picture of defect motion and dislocation motion to amorphous system, and it's going to be difficult because in ordered systems you have a regular lattice with respect to which one can identify the defects, okay? But in the case of amorphous system, there is no underlying lattice. So the question is, like, how do we extend this notion of defects to glasses? Are there defects? I mean, can we, like, identify defects in these systems by looking at the structure is the question that we want to answer. So the two main questions that I'm going to delve upon is what are analogs of defects in glasses, and how does it, is there a correlation between structure and then plasticity in these systems? So when so what I'll do, like, in the next few slides is I'll take you through slowly through, some of these ideas that have been developed over the years, trying to understand, like, how deformation occurs in these glassy systems. And one of the earliest idea that came about in this area, like, disordered systems, is based on this free volume proposed by Franz Papen. And again, like, this model was motivated by Turnbull and Cohen. Like, they were trying to develop a theory for glasses, like, based on free volume model. And this is once again, like, they extended those ideas to understand how deformation occurs in disordered systems. And once again, when you talk about disordered system, as I said, like, the configuration is amorphous. There could be, like, certain regions that are loosely packed, and there could be regions that are tightly packed, okay? So it's a very intuitive picture, like, intuitive model. So when you apply stresses, like, probably, like, you can imagine that there are certain regions that are loosely packed, and those are the ones that are going to fail, okay? So, and when you say loosely packed, once again, like, this idea of, like, free volume, like, it comes naturally, like, as the agent to, like, a structural measure to look at. And what he said was essentially, like, this atom is going to move under, if you apply stress, this particle is going to move only if there is sufficient volume, available to it. Otherwise, it will not move. And then based on that, they develop this kind of model. This is, like, the strain rate, like, how the deformation rate occurs based on these parameters, okay? And essentially, yeah, so essentially, like, this model takes into account the free volume available in the system, and based on that, it predicts what is going to be the shear rate if you apply a certain strain rate on the system. And now, like, this was the first set of ideas, and then, like, these ideas were taken forward by Bulatov and Augen. They made, like, certain modifications to this model. What they said was that, like, if you have a local deformation, like if a particle is moving from one, if a certain neighborhood is getting deformed, then the attempt rate, for those local inelastic transformations is given by this, this is based on the transition rate theory. One can write the rate of these transformations in this fashion, and delta is just the free energy. So delta G is the free energy barrier that one has to surmount to see these rearrangements in the system. And this delta G is essentially when you apply stress on the system, it is getting lowered because of the applied stress in the forward direction. Okay, so that is what it says. So when you have an applied stress on the system, they can, the free energy the energy barriers get lowered, and then there will be more rearrangement. That is what this equation essentially says. And one of the important elements that he introduced here is that he brought in this idea of elastic deformation. So whenever you have a rearrangement, you are storing elastic energy, and this will get dissipated in a certain way. Okay, so this is the energy gets dissipated. The stress has to get redistributed, whenever there is a flip, and that has a long range nature. Okay, the stress relaxation. So essentially what he said was that, let's say you have a volume 1, and then there is a strain volume element omega 1, and then you are applying a strain epsilon Eij on that element, and it's going to deform in this to this shape like omega 2 with a stress sigma ij, and then he showed that one can relate this sigma ij, the stress that is developed in this, based on this equation. And we don't have to get into the details of that. What it essentially says is that the stress decays it has a long range character. Okay, so that's the key point here. One can write down these nice elasticity equations and then show what is the green tensor that is relevant in this equation, and it has a long range nature. And for certain geometries, you can show that what is done here is you have a spherical inclusion that is strain, and then you are looking at the far field strain decay, and this has a quadrupolar structure. Okay, so this is once again the solution corresponding to linear elasticity equations derived by Eshelby. Okay, so this was one of the important addition they made to this contribution they made to this problem, Argon and Bulatov. And now these ideas became very popular. So in the recent years there have been a lot of MD simulations on plasticity of amorphous solids, and this is this is a strain stress and then strain curve that you notice in a simulation in MD simulations. And what you see here is these are all quasi-static deformation simulations and done at temperature 0. What you see here is that it's not a smooth line like the one that I showed earlier. So there are a lot of serrations along this. There's a rise in the stress, but these are punctuated by a lot of these serrations. Okay, so what happens is you apply stress on the system. There is a elastic loading, and then suddenly there is a plastic drop, because of which the stress decreases, and then once again there's whenever the stress drops, there is a redistribution of the stress, and then once again there is elastic loading. So this way the system the plastic deformation or the deformation in the system proceeds in this fashion, so elastic increase, and then a plastic drop, elastic increase, plastic drop. So whenever you have this plastic drop, when you are in this transient regime, when the strain are very small before the system has attained a steady state, if you look at what happens when one can, these are all MD simulation, 0 temperature, you can write the Hessian for this and then diagonalize, find out the eigenmodes, and you look at the lowest eigenmode that goes to 0, and then if you look at the structure of that eigenmode, it has this kind of a structure. What you're seeing here is the displacement vectors. Okay, so whenever there is a plastic drop, you can see the lowest the structure of the lowest frequency in the system, and then this has a quadrupolar structure. This is what you see when you look at the displacements. Now this is at small strains. However, when you go to steady state, it's not just one isolated event. You have multiple events occurring at whenever there is a plastic drop, and there is essentially a cascade of drops in the steady state. So these are the characteristics of plastic deformation that were discovered in this paper. There was a lot of focus on this, but then this particular paper brought all these things very clearly. So I mean, I'm just taking you through like, how deformation occurs and what has been done so far and then what we are going to do further, okay? So once again, like, all these were simulations, and now like there were some experiments done using colloidal glasses. These are dense colloidal suspension. You can do shear measurements and then look at do local level, like, particle level strain, okay? So yeah, so I mean, if you want to do these kind of things in atomistic systems, experimental systems, it's going to be very difficult because we need to resolve the motion of single particle, but in colloidal suspension, these particles are larger. We can use microscopy to visualize, like, what is the local strain field in these materials, and then what they showed was that essentially, like, you have this kind of a quadrupolar structure whenever there is a shear transformation occurring. So for example, what is happening in these two steps is you're looking at this zone, and then you see that this is at strain gamma 1, and then this is at strain gamma 2. As you strain, like, further, what you see is that there is a red, like, high strain event occurring here, and then it is associated with this quadrupolar structure, okay? So which was also predicted by Eshelby's which is also predicted by Eshelby's solution. So these were some of the first observations on the characteristic of water plasticity carriers in these systems. So once again, yeah, so later on, like, we use this kind of a correlation function, strain correlation function. A here is the shear strain. I mean, one can compute the strain tensor based on the, you take a particle and then look at the relative displacement of this particle with respect to the neighbors, and then one can extract a strain tensor from this displacement information, and then one can plot different components of the strain. What is plotted here is the shear strain component, and then epsilon is the correlation of the shear strain. This is the xz plane. So epsilon xz, what is being plotted here is correlations of epsilon xz, and then if you look at these correlation functions, once again you see this nice quadrupolar symmetry. What it says is that essentially all these shear transformations, or the zones that have high strains, those correspond to something like Eshelby's inclusion in this material. So that's what it says essentially. So you have like, high strain, and then, like, the surrounding material, like, the surrounding matrix has elastic character. So because of this transformation, it has this kind of quadrupolar strain decay. So that's what it says. Yeah.
See similar structure in that normal components as well, like in the strain tensor?
They have different symmetries. So yeah, so based on the symmetry, like, we see the we have done actually compared experiments and simulations. I mean, we get similar results. Whatever, like, response you see in simulations, I mean, we can see the same response in experiments too.
Okay.
Yeah.
But those are different from this one, because here only the correlation is between shear.
Yeah, exactly. Yep.
Thanks.
So now these were, like, some of the ideas. What we learn from these from this thing is how does plasticity occur, like, in these systems. Essentially, like, you don't have dislocations. There are, like, group of particles within the system that locally, like, deform or change their neighbors, okay. So there is localized deformation in the system. So all these red zones, like, they show like local deformation in the system. That's how, like, the disordered system is going to deform when you apply stresses on them. Like, there are, I mean, in the case of the crystals, like, you have these dislocations that travel from one point to the other, but in this case, like, there are the dislocations are these shear transformations, okay. That's how, like, they are the plasticity carriers. That's how plastic deformation arises in these systems. Now the second question is, what we have done so far is, like, we have characterized, like, how does deformation occur in these systems, and what is the characteristic of these plasticity carriers. Now the second question that we want to answer is, if there is a, like, shear transformation here, we call these high strain zones as shear transformations because they are the ones that are carrying plasticity. So if I see a shear transformation here, like, the second question is, like, why does it form in this particular zone? Is there something special about this zone structurally that the plastic event occurs here? So that's the question that I'm going to answer. How is the structure related to local plasticity? That is the question that we want to answer. And before I answer that question, I would like to take you through some of these ideas that were proposed very recently. So structure, like, I introduced the first structural measure that I introduced was free volume. And there have been a lot of experiments, colloidal experiments and simulations. They have not found a strong signature between these shear transformations and local free volume, okay? So naturally, like that made us look for other structural measures to correlate the structure to plasticity. And this was one of the ideas that was proposed in the context of relaxation of glasses, okay? There is no stress. The rearrangements or the relaxation is occurring due to thermal fluctuations. So the idea here is that once again, like they wanted to capture the structural aspects. Where do these rearrangements occur in the system due to thermal fluctuations? Okay, and to characterize the structure, they use this kind of they used this kind of structure functions. So this is G, like it characterizes. So there is this Rij sitting here, like it characterizes the structure as a function of distance from a tagged particle, and then there is this Psi, like which takes into account the angles between the particles. Okay, so essentially, like there is information about radial distance, and then there is also like information about the angles in these structure functions. And then what Andrea Liu and her co-workers did was that they fed a lot of simulations data to this machine learning techniques, and then made the technique learn like how where the deformations or the particle rearrangements occur, and then based on that, like they predicted how like they predicted something called they calculated something called softness field. Okay, based on the structure functions, they calculated a softness field. The softness field tells you like the regions in the material where the rearrangements can occur very easily. Okay, so that is what is the softness. Essentially, like you can think if a region is soft, that's more susceptible to rearrangements. Okay, so that's the kind of quantity they came up with. It's a structural measure based on these structure functions. And now what they did was they computed two things. One is PR is rearrangement probability based on the softness. Okay, like you can calculate the softness for each and every particle based on these two structure functions, and yeah, you can associate a softness value to a particle and then see whether as a function of this softness, how does the rearrangement probability depend on this softness. Okay, and then what is plotted here is once again what you see here is that as the softness increases, the rearrangement probability increases. What it means is that softer a particle, the larger is the probability for that particle to rearrange. Yeah. Once again, like yeah. Maybe we can talk about this later. Like it will also take me. It will take me a little time to recall. Like so, they essentially make a hyperplane, and then like they look at the distance from the hyperplane. If it's on one side of the hyperplane, they call it as fine. So yeah, so like so this was a very nice structural measure using which like they could characterize this rearrangement probability very nicely. And then once again, like here what you see is that the delta E, the energy required, the energy that you need to surmount to see a rearrangement as a function of the softness. So as the softness increased, the energy barrier that you need to surmount to see a rearrangement was going down. Okay, so this was a very nice result. However, like this was all based on machine learning techniques, and if you start thinking about what this softness parameter is, like what is it motivated, what is it capturing, like trying to give a physical meaning to this softness parameter gets a bit little difficult. Okay, so since these structure functions are dependent on essentially particle coordinates, so okay, fine. So let me present this before I go further. So once again, like these ideas found support even in experimental systems. These are experiments done by Rajesh and his co-workers. I mean, and what they saw was that they initially started with amorphous configuration. They characterized based on the structure of the particles. They characterized the local softness of each and every particle. And the pink, the background that you see here is the softness field. And on top of that, what they are showing is if you start with an amorphous configuration and you let the system relax, what happens is after very long time scale, several relaxation times, you will see that the system crystallizes. Okay, and then these crystallization, the crystallites, The particles that form crystalline configurations, they appear in these zones where the particles were softer, okay. So you have a reference configuration with respect to which you calculate the softness, and then you look at the system, you wait for several hours, maybe 100 hours, that's the kind of time scale that they have waited here. And after that, you see, what is the configuration of the system where the particles have formed crystalline patches, where the crystalline patches are formed in the system, and they essentially appear up on these regions where the particles are soft. So yeah, so there were there was a lot of this idea was very popular. So now the question was, as I said, all this is the softness function is calculated based on the structure. Okay, essentially all that you need to know is where the particles are sitting. So what Sarika and her co-workers did was they came up with a microscopic theory for softness. Okay, so now they developed a new softness measure. They called it as softness, but it's not the same machine learned softness. I'll tell you a little bit more about what this softness is based on a microscopic theory, and they were essentially able to see the same results that they found in machine learning things. So what it says is that now we have a softness measure that is derived from a microscopic theory, and then you can understand it well. Appreciate it well, you know what you are computing, okay? Unlike in machine learning techniques where it becomes very tricky to associate meaning to what is being computed. So this is what I'm going to talk about. So these are simulations, and then we have done some experiments based on these ideas. I'll tell you what these ideas are, and we have used colloidal suspensions to validate some of their ideas in experiments. So we have done experiments under shear and also under rearrangement and due to thermal fluctuations. Okay, so these are the kind of systems. I'm going to skip this part so that if you have any questions, you can ask me. These are just colloidal suspension, 1 micron particles, and then they are Brownian. You can see at very high densities, all that they do is they jiggle around their mean position. So they are big, and then they contain fluorescent dye. We can see these particles in 3D. Okay, so not only on a single layer, but you can see in 3 dimensions how these particles move. So this is the kind of system that we have. 7%. Yeah. We don't have a right number because maybe I'll tell you later. So. Sometimes, but you see that if you look at this configuration, you don't see too many crystalline patches. So yeah, it's not you don't see too many crystalline patches in the system.
Okay,
yeah.
Thank you.
We just mix 2 batches of particles and then some are suppressed.
Okay, so basically, it's a bidispersed mixture.
It's not a bidispersed mixture. It has 7 to 10%. Yeah.
So that's the natural polydispersity of a PMMA.
Yeah, exactly. Cisdecylin and CHP. Yeah. Yeah, so this is the kind of system that we have for shearing the system. The bottom boundary is kept constant and the top boundary is moved with a constant velocity. We are applying shear rates, constant shear rate in the system, and the shear rates are in this this is the magnitude of the shear rates that we are using in the system. And we are tracking large number of particles, close to 250,000 particles. And this is the kind of system that we have. We can, as we shear the system, we can see, we can record the images of the particles and then see, how they're moving in 3 dimensions. If you look at a typical particle, how does it move? On some small time scales, you see that it's jiggling around a mean position, and if you allow sufficient time, it will escape and then go to a nearby cage and then do this kind of motion. Okay. So once again, one can extract a relaxation time scale from that thermal motion. So that turns out to be 20,000, and then this is the applied shear rates are in this are of this values, and then one can estimate what is a modified Peclet number. This is just the product of these 2 time scales. Gamma dot and then the time scale, and the Peclet number turns out to be 1, which is weakly driven. These are not strongly driven systems. So these are the kind of systems that we are looking at, and if you look at the shear rates that we are working at, and what is being plotted here is the displacement of the particles. This is the kind of geometry that we have, one of the plate is being moved and the other plate is stationary. This is a plane shear, and if you look at the displacements of the particles as a function of distance between the boundaries, you see that there is a linear displacement profile. There are no shear bands in the system, it's a homogeneous flow. So now, what we want to do is we want to relate the rearrangements in our system to the structure. So the way we do it is, I'll not present all the details, but tell you the important points so that we understand the idea that is involved here. So you take n body system, and then what you can do is using mean field approximation, you can say that within the mean field approximation, you can look at a single particle, the fluctuations of single particle, and then you are essentially freezing the surrounding particles and then coming up with an effective potential that a particle feels due to the presence of the rest of the particle. That is the mean field assumption. Okay, so you can start with this is this goes back to that Fokker-Planck equation, BBG by hierarchy kind of thing. You have evolution equation for each and every particle, and then you can reduce it to a single particle with an effective potential. So that is the idea that is being used here. So you take any tag particle, it sees you can make mean field approximations and then say that this experiences a caging potential because of a frozen background. So that is a kind of a picture that is presented here, and this is based on mean field approximation. And now what is the what is this potential? So that's what we want to understand. Okay, so based on mean field potential, we come up with these mean field ideas. We come up with this idea. Now the next thing is what is this effective potential that a particle is feeling, and we go back to these ideas of Ramakrishnan and Yusuf. They proposed an expression for the effective potential based on liquid state theory ideas, and I'll just show you what this expression is. So this is the expression for the effective potential that a particle feels, and C of q is the direct correlation function, S of q is the structure factor, C of q is dependent on S of q. So essentially, if you know the structure factor, which is essentially all you need to know is the structure in the system. So if you know the structure in the system, then one can derive what is effective potential in the system, and what is being shown here is that effective potential. Okay, based on this information, the structure factor, one can derive what is effective potential in the system as a function of density of colloidal particles. Okay, so you can see nicely that when the density is low, the effective potential is shallow, and as you make the density higher and higher, the colloidal density, the effective potential becomes deeper and deeper. Okay, so one can one can use this kind of expression, you make a harmonic approximation, you say that your effective potential has this form, harmonic form, and essentially the curvature of the potential is the structure factor, the structural order parameter. Okay, so this is inverse of the stiffness of the potential. Okay, so what we are essentially deriving from here is the stiffness of the potential. We are taking an inverse of that, and we are calling that as our structural order parameter. Okay, so so this S, which is the structural order parameter, this is essentially the inverse of the curvature of the caging potential. If you look at this as a function of phi, you will see that as you increase the density in the system, the structural order parameter, what it tells us is that the susceptibility to a rearrangement, how soft or how hard the local neighborhood is. Okay, this is not a local neighborhood, this is averaged over all the entire system. Okay, so what is the stiffness of this effective potential is what it is saying. You are taking an inverse of that. So you are essentially looking at 1 over the stiffness, so which is essentially softness. Okay, so let me use the word softness so that it is easy to understand. So we are looking at 1 over the stiffness, inverse of the stiffness, which is the softness. So S is essentially the softness, but this is based on, not based on the machine learning technique, but this is based on the caging potential. Okay, the softness is derived from the caging potential, and one can show that one can extract the curvature and also the depth of the potential. You can see that they essentially they are linearly dependent on each other. So what we say is that instead of looking at the curvature, one can look at the depth of the potential. Okay, so the inverse of the depth of the potential is going to be a structural order parameter. Okay, so essentially whatever information is there in the curvature, it's also there in the depth of the potential because of this linearity. So now this is the whole idea. Okay, so now what one can do is this is based on Q space. Okay, which is you are taking into account the entire system. Now we want to extend these ideas can be extended to a local particle level, okay. So defining SFQ on a local level is going to be hard. So what we do is we go to real space and then we can show that the depth of the potential is essentially given by CFR and GFR. GFR is the pair correlation function in the system and the CFR is related to the pair correlation function in this fashion, okay. So now what we can do is based on GFR, we can find out like what is the stiffness or the inverse of the stiffness, which is the softness for our system on a particle level, okay. So since GFR can be evaluated on a particle level, we can also compute like what is the softness on a particle level. So if you look at the, this GFR is essentially mollified, like otherwise if you look at the bare GFR, it has a lot of fluctuations, and what we do is we do mollification using this kind of a function, and you see that depending on this sigma, you get you do mollification at different levels, and then you optimize the sigma so that you you retain some of that some of those local density fluctuations, okay, and that's how you come up with the optimal value of sigma, and that's the sigma that we use in our experiments. And so what we do is that using this formulation, what we can based on the structure of the particles, coordinates of the particles, we can compute what is the local caging potential, what is the local stiffness, or the inverse of the stiffness, which is the softness, okay. So first what we thought was let's apply these ideas to crystals. There is nowhere in this formalism it says that it's applicable only for amorphous systems. It is equally applicable to ordered systems also. So first thing what we did was we took a defective crystal, and then we so a conventional way of identifying defects in this system is based on this bond order parameter, okay. You look at how you connect neighboring particles using bonds, and then you look at how these bonds are oriented. Based on that, you can identify the defects in the system, and this is a conventional way of doing things. And what it essentially says is it gives you information about the geometry, nothing else, okay. So now we do we calculate the structural order parameter for the system, and then it also captures all these defects very nicely. Now what is interesting about this is the structural order parameter or the softness that we calculate in our system gives us information about the local softness, okay, local caging potential. So it is much more it's giving you much more physical insight into what these defects are. The other the bond orientation, it just gives you information about geometry. Okay, so it works very well for crystalline system, and we can also do this for a 3D system, and you can see that it captures very well these grain boundaries in 3D systems also. So that was very nice. And what we do here is we take a colloidal monolayer, a binary mixture of colloidal monolayer. So it's not a 3D system, it's a monolayer, but it's bidisperse. We kill crystallization by taking bidisperse system, and this is at a density of 73%, and what we have done is we have essentially calculated the local level softness or the structure order parameter for this for these guys, and you can see that there are regions that are hard, there are regions that are soft, and to characterize this in a better way, what we do is we can look at the distributions of the structure order parameter or the softness in our system, and what you see here is once again as you increase the density, the curve shifts to lower softness or lower structure order parameter. What it says is that as you increase the density in the system, the overall softness of the system is getting lower. It's lowering. Okay, so that's why the distribution is going in this fashion. One can look at the average of these things, and then you see that as you increase the density in the system, the softness or the structure order parameter in the system also decreases. Okay, so now what we have done is we really wanted to understand, now that we have particle level information, we wanted to check. We had this idea so if you have rearrangements in the system, if you have amorphous configuration, there could be certain regions that are soft, there are certain regions that are hard based on the local configuration, the local neighborhood. Okay, so just to check that, what we have done is we picked all the soft particles in the system, and we grouped all the soft particles and then all the hard particles in the system, and then we looked at the local GFR for hard guys and then the soft guys. It's an averaged plot for all these particles, and then you look at GFR for the particles that have larger structure order parameter or some with the particles that are soft, and then particles that are hard. You can see that hard particles are associated with a more structured environment. Okay, so this goes by. I mean, this confirms our intuitive understanding of the disordered systems. You know, there are certain regions where the packing is loose, and then there are certain regions where the particles are tightly packed. So in those regions, I mean, the hardness, like, you know, the system should be hard, and then the particles where the regions where the particles are loosely packed, it should be associated with higher softness. Okay, that's what it confirms. Okay. So now, like, you know, yeah, with with decreasing softness, we also see that the relaxation time in the system also shoots up. So yeah. Let me go to next thing. So, yeah, how many minutes do you have,
Yeah.
Shantan?
Thank you. Yeah, so, yeah.
Oh, more than.
Okay. So see, I just wanted to ask you, so these are very, very dense suspensions, right?
Yeah.
So we know from Wilson Poon's very famous paper that, you know, the systematic errors can easily be 3%, 3 to 6% in measuring the, you know, the volume fractions of very dense suspensions. So I just wanted to comment, I mean, can you put an error bar on these concentrations that you have, the densities that you showed us in the last figure? I saw 70
yeah,
and
so
73.
This is something, yeah, this is something that we can do.
Yeah.
Yes. Yeah.
No, but I just wanted to ask you, so I mean, what are the error bars on the density?
So we have not looked at the error bars, but I mean, what we see here is, you know, there is a, like, you know, a trend, like, you know, with changing area fraction that gives us a little confidence, but of course we can go back and then put error bars on them and then see, like, you know, what's happening. But this trend, like, you know, I mean, is something that is seen in experiment simulation, so if you were happy.
Sure,
but
no, I
mean,
just wanted to know how you...
No, sure, like, you know, we can do that. Like,
no,
you know,
what is the experimental protocol in calculating the density of the suspension?
So the density of the suspension, so using images you can
so you're counting
track, like,
particles,
we are counting the particles, and then, like, the manufacturer, we have the radius or the size of these particles from manufacturers, and
okay.
We input
so
those
you're
values.
not really considering the nonlinear effects at these very high volume fractions?
No, not really.
Okay,
Yeah.
thank you.
Yeah. Yeah, so now, like, you know, so far I've spoken about how to characterize the structure in the system. So next part is how to correlate the structure to the rearrangements in the system. So the rearrangements can occur for two different reasons, either due to thermal fluctuations or due to applied shear in the system. So first, what we are going to take a look at is the rearrangements that occur due to thermal fluctuations in the system. And what I'm showing here is, like, you know, how do we identify rearrangements in our system, and that is based on the cage relative displacement. Okay, I've not given the expression for delta CR. So essentially you have a particle and you have the neighbors. You look at the displacement of this particle with respect to the neighbors, okay, the first nearest neighbors. They are identified using the first minima in GFR. So you identify the first nearest neighbors, and then you calculate the cage relative displacement of the particles, and that's what is plotted here as a function of time. And at small time scales, you see that there is this caged motion. This is at the dilute 60%, okay, this is not 60, 0.6, I would say. So this is the dilute, the most dilute solution, the most dilute system that we have in our system. And yeah, there is, like, a small subdiffusive regime. And then if you wait for a longer time, like, you know, there is once again, like, you know, a slope of 1 that is coming here. So there is a crossover from subdiffusive to diffusive regime. So we take this crossover point as the characteristic time scale in our system, and then this is the characteristic displacement in our system. Okay. So on this time scale, if a particle has a displacement that's greater than this, then we call it as a rearrangement. So that's how, like, you know, we identified rearrangements in our system. And the first thing that I'm going to show here is, like, you know, the distribution. This is P of S, the distribution of the softness, and then this is the distribution of the softness of the particles that are rearranging on over a certain time scale. Okay, over a time scale, like, you know, this is those notations are missing. This is tau r. Okay, and then this is some displacement scale. This gives us the displacement scale, this gives us the time scale. So on this time scale, we are looking at the rearrangements, and then we are plotting the distribution of the structure order parameter or the softness for those particles, and you see that their softness is larger. Okay, so if you take the mean of this curve, okay, for all the particles, and then you draw a line, and then, like, you know, in the red curve, like, you know, there are 90% of the particles in the red curve have softness greater than the bulk softness or the average softness in the system. So what it means is that essentially the rearranging particles have higher softness or are associated with a higher order parameter, higher structural order parameter. So now, so this is one way of correlating the structure to the rearrangements in our system. The second way is looking at the rearrangement probability. Okay, so once again, this is computed as a function of the order parameter or the softness in the system. So you see that smaller at the rearrangement probability increases with increase in softness. What it says is that softer the particle, larger is the probability that a particle with larger softness will rearrange, okay? And this dependence diminishes as you go to lower densities, okay? If you take suspensions that have lower densities, then this dependence on softness becomes very weak, okay? So this once again, what it says is that if you go to higher densities, the correlation between the structure and then the rearrangements becomes stronger. Okay, so these are the kind of things that we can understand using our colloidal experiments, and this is just a visual impression of whatever is presented here. So we take a reference configuration, and for that we compute the softness or the structure order parameter, and that is the contour plots that you are seeing here. And then with respect to this configuration, we wait for for a time scale tau r. Okay, the tau r goes back to here. Okay, on this time scale. We look at rearrangements on this time scale with respect to a reference configuration and identify the rearrangements in the system, and you see that most of them occur on these regions where the system is very soft or associated with higher structural order parameter. So I mean, what I've established is when you have rearrangements, what I've established is a strong correlation between structure and then the rearrangements under in Poisson systems, and the rearrangements here are occurring due to thermal fluctuations. So now what we want to do is we want to extend these ideas to sheared systems. Whether we can see similar kind of structure order correlation. So in sheared systems, what we are doing is once again, we need to identify the rearrangements, and what I'm going to tell you is how do we identify the rearrangements. And this is based on the non-affine displacement of the particles. You have a particle, and then you have the neighbors. One can, by doing microscopy, one can compute the non-affine displacements. So this is the recipe, the recipe for computing the non-affine displacements is given in this particular paper by Falk and Langer. So essentially what you're doing is you're subtracting the affine component, which is the trivial component due to the applied shear, and then whatever is remaining is the non-affine component, okay? So essentially if you have a displacements of this form, then this is affine, but then in disordered systems, most often what you have is you have deviations from affinity. So what we're computing is the deviation from affinity, and that is the non-affine displacement in our system, and based on this non-affine displacements, we're going to identify rearrangements. So once again, I showed you this movie in the beginning of the presentation, and what was plotted here is essentially the non-affine displacements in our system. So once again, what we do is we are shearing the system, and at different stages, we can compute the non-affine displacements around this is computed at strain gamma, taking a strain window of delta gamma. At around each gamma, we are taking a certain small strain window, and we are computing the non-affine displacements around that strain value. And this is delta gamma with respect to gamma, okay? And then we look at these non-affine displacements. Once again, we identify a time scale and then a length scale, not a time scale, the strain scale, okay? Here strain scale and then the time scales are linearly dependent, so one can easily replace this with time scale. So we identify a strain scale based on the transition from subdiffusive to diffusive regime. So this is the point where we say it's going from subdiffusive to diffusive regime, because this is where the slope is becoming 1, okay? So we identify this strain scale, and we also identify the scale of the non-affine displacement. So if you have a particle, if you look at the particle motion over the strain scale, delta r, delta gamma r, and if a particle has a non-affine displacement greater than this, then we call that particle to be rearranged, okay? That particle has undergone rearrangement. That's how we identify rearrangements in our system. So the first thing that we did was we plotted the distribution of the structural order parameter as we strain the system, okay. So these are distributions of the softness or the structural order parameter at different strain values, starting from very low strain value to steady state, okay, 60%. You see that when you start start to deform the system, and then as you go to larger and larger strain, this is like, there is a slight shift to the right, which means that the average softness of the system or the average structural order parameter is increasing. So one can, whatever information is there in this plot, one can look at the deviations from, we are not looking at S, the averages, but then we are looking at the deviations from averages, okay. Each plot is going to give us a certain average value of the structural order parameter. We look at the deviations, okay, with respect to gamma 0, which is the first frame, okay. So we look at the deviations of this change in softness or change in structural order parameter, and it is plotted as a function of gamma, okay, as you strain the system. And you see that what is happening is, as you strain the system, these are different strains, and after about 20%, there's a linear increase here. It appears to be linear, but we don't know what is the trend. But after a certain gamma, the system saturates, okay, which means that it enters a steady state. These are the yellow points, okay, that are these are the square, the black squares that correspond to the change in softness of the system, change in the order parameter of the system. Now what is plotted on the right axis is the non-affine displacement as a function of gamma, okay. So what we have done is, once again, we have done this kind of calculation, okay. Around each gamma, we have taken a window delta gamma, and then we have computed what is delta, the non-affine displacements, and we have taken the deviations, and whatever is done here, the same thing is done here. So you see that even the non-affine displacement show, the non-affine displacements characterize the dynamics in the system. Okay, just give me 2 minutes, I'll be done. So what we see here is that the non-affine displacements and then the structure order parameters seem to follow each other, okay. So they yield and then saturate at the same point. What it says is that essentially there are the softness and then the non-affine displacements are correlated, or the plasticity in the system is correlated. So what I'll do is I'll just end my talk with this slide. What is shown here is we take a reference configuration, we compute once again the softness of the order parameter for the system, and that is what is the contour here. And then we strain the system with respect to that reference configuration, and we pick out only those particles where the rearrangements that are rearranging, okay. These are the particles, the white dots are the particles that are rearranging. And as we progressively strain the system, we go to larger and larger strains. There are more and more particles that are rearranging or showing plastic behavior, and then they seem to pop up in this region where the order parameter or the softness is large, okay. And yeah, so essentially what we have established is that once again, even under shear, the rearrangements are determined by the structure, okay. So this is a movie, a small movie of what was shown in that those images, okay. So we can very nicely capture where these rearrangements are occurring. They are occurring in regions where the caging potential is shallower, okay, or the order parameter is larger. With that, I would like to thank you for your attention. And these are the conclusions. I would leave it and take questions from you.
We have time for a few.
These rearrangement zones that you see, so this would be, have you looked at the aging of the sample, and do these rearranging regions, do they, increase with...
Yeah, so this is essentially going back to Rajesh's work, I would say
using your softness potential.
We are looking at that, yeah.
Okay.
We have not, done that so far, but
okay.
Yes,
Yeah. So can you, for instance, as you approach the, the kind of the kinetically arrested state, can you think of a kind of a diverging length scale, like a static, like a dynamical correlation length?
Yeah, this is the first thing that we have looked at, and going forward, we will probably look at some of these questions. And
okay,
I'm not a glass expert, okay. I know how to shear glasses, but not really looking at those length scales. So, but for sure, yeah, that would be something interesting to look at. Yeah.
Okay, thanks, Vijay.
So I had just one question that since you have these soft regions developing, percolating through your system, can I expect or have you seen anything where fractures would appear perpendicular to those soft zones? Suppose you, I mean,
Yeah,
one
so
would
we are
expect-
looking at those aspects, the anisotropy aspects, even in these rearrangements.
I mean, if you were to expect fracture at some point of time or cracks, then I would expect that the non-soft regions would be the first to break under some sort of thing, and that could also be a pointer to your experimental pointer to where the soft zones are.
These are results like, this
on
is like a
computer simulations, but
this is like a cake fresh out of the oven. Okay, so we still have a lot of time to
Thank
bake
you.
more cakes out
yes,
of it. Yeah.
thanks.
Other questions? Okay, if not, I'll ask one. So, for very small strain, I'm talking about the last part. Part of your. So, small strain also you see some plasticity. I was wondering that that
Yeah,
linear
so
response
let me
should-
clarify that point. So you see here, like, the non-affine displacement for, this is like, very small gammas, okay, small strain. So when, like, in the transient regime, around about a value gamma, like, you take delta gamma and then you look at the non-affine displacement. And when your gamma is very small in the transient regime, you don't see any rearrangements at all, okay. So whatever data that I've showed you here in this movie, this is like, gamma corresponding to the steady state, okay. So around each gamma, we are taking a delta gamma window and then looking at the rearrangements. So yeah, so in the transient state, like, if you look at the same strain scale, then the number of rearrangements that you see is very, very small. Yes, this we have seen even when you look at the raw data, you will see that there are very few rearrangements in the system.
Okay.
Yep.
Thanks. Okay, let's thank Vijay for a wonderful talk.